Um, Thank you for staying for the last talk. And the one advantage of having the last talk is you don't have to motivate your problem because people have already done a good job of motivating. So today I'm going to present you algorithms or for information set decoding. So the problem that cryptosystems, that code-based cryptosystems should care about. I go directly to the problem. This is called the ISD problem that you've heard. So the problem is formatted as follows. You're given a matrix H, which is a parity check matrix of a code of dimension n minus k times n, and the syndrome. And the problem is to find an error vector E such that H times E is S. So this is basically what you have to do to decode a random code. And also we assume that we know the weight of the error. So for us it will be some constant times n, where n is the dimension. And this is without loss of generality, because even if we don't know m, even if we don't know w, we can always brute force and repeat the algorithm basically polynomially many times to get the correct weight, Hamming weight of the error. Why do I say that the polynomials factors do not matter? Well, they do not matter because all known algorithms have complexity 2 to some constant times n plus some small o of n, so we are ignoring polynomial factors in n here. And what we want to do, we want to know what is the best constant here is. So you've noticed that the problem is parameterized by 3 integer numbers, which is n, k, and w, and the complexities are expressed only in one of these parameters, which is n. And this is true because we assume the worst case hardness. So the worst case is both for omega and for k. So that's why we can always express the running times as just 2 to the c times n. So what are these constants? Just let me give you some overview on known algorithms, both classical and then quantum. And the way of presenting algorithm will be chronological. So this line will go from old results to recent results, so the numbers will be decreasing from left to right. So what we start with is the first algorithm is due to Prange, which just basically enumeration. So what we take is we take our unknown vector E and we enumerate. And the running time exponent, the constant in the exponent, which is the C, I mentioned on the previous slide, will be, well, 0.120. But this is the generic enumeration algorithm. So what we can do also generically is meet in the middle. And well, this was proposed several decades later, basically reducing the ISD problem to the collision search between the two lists. Now, even more generically, even more decades later, there exist algorithms to prove generic collision search between two lists improves in memory. And this is where it's well known as Shamir-Schreber trick. And this is using some other techniques which call representation techniques, we can solve ISD based on collision search between the 4 lists. Now, all these algorithms, all these collision search algorithms, they basically can be phrased as doing an exact collision search between 2 or more lists. And only very recently it was actually recognized that the ISD problem is not the exact search, but rather an approximate search. And this was mentioned, and it was done by the series of work by Alexander Mai and his students, with the recent result presented this Monday by Mai and both, and this is how these constants have decreased during the time. Now, this is all classical, and what can we do quantumly? Well, unfortunately, or maybe fortunately for constructing, these all algorithms are inherently combinatorial. And quantum algorithms are not particularly good at speeding up problems which are not number theoretical, ideally with a commutative group. That's not the story here. Here we are really in combinatorial regime, and we can't do much, but we still can do something. And okay, what can we do? So the first algorithm is, well, enumeration. enumeration meaning there is a for loop. If there is a for loop, we can use Grover. And that was presented by Bernstein at PQ Crypto 2010, where we just take the enumeration space for the error vector and we apply Grover on it. That gives you yet another quantum exponent. So the line below will be describing the constants in the quantum setting. Now, with the collision search, the situation is a little bit more difficult than just Grover. Yet, there exists quantum algorithms, what's called, in quantum world, it's called element distinctness, which is based on what's called quantum walks, and I will describe quantum walks later. And it was realized that all the collision search algorithms can be also speed up in quantum setting by using this element distinctness algorithm, and that was presented at last year PKC by Kachigar and Tirish. And in that paper, they posed as an open question, how can we speed up the approximate search? The reason why it worked, or the reason why we could apply the quantum collision searches is because the search was done exactly. So as I said, in 2-list and 4-list collision search, we search for the exact match. Now, the near neighbor search does not search for the exact match, and it's absolutely not clear how to use quantum walks for the approximate search. And this is basically what I'm doing in this work. I'm answering the question of how to combine the near neighbor results, the near neighbor techniques, with quantum walk. What I should say is that it gives a slight speed up for the near neighbor search over 2 lists. My open question, which I will not be talking about in the last slide, but rather now, is whether this gives any speed up for near neighbor search for 4 lists or more. Now, the reason why it's absolutely not clear is that because all these problems, all these near neighbor search problems, they become a big optimization problem with various parameters, and eventually starting from near neighbor search on 4 lists, the optimization problem becomes a mess. And it's absolutely, there is no intuition why this particular choice of parameters gives the best algorithm. That's why I leave it as an open problem, not because it doesn't work, but that because it's hard to say. What I also should mention is that at my first of the submission, when I submitted the paper, I also thought that one could improve the 4-list algorithm, but then I found a mistake there, so I would refer you to the full version of the paper, where I explain why the numbers are like that. And also, one thing I should mention is that all of these algorithms, both classical and quantum, except the two leftmost algorithms, they use exponential memory. So they also use the memory of 2 to the constant times n, and in case memory is expensive, this all might not make sense. Well, it does make sense in the model we are using, but the memory in these algorithms are also exponential. Okay, so what I want to present, so anyway, the result is that we can use the near neighbor techniques, which I will present in quantum setting. So for that, what we need is we need to actually analyze what's called locality-sensitive filtering techniques, or LSF, for the Hamming metric. And then I will explain you how one can use this for the ISD algorithms. Now, before I want to do that, I want to explain you the algorithm, the 2 collision search algorithm, and then how we can tweak this to get the near neighbors inside. So this is the algorithm, the two collision search for ISD. This is recall the problem. You're giving H and S. You are asked to find the error vector E. The first step of all of these algorithms, of really all the algorithms I showed in the previous slide, is first to bring the parity check matrix H into the systematic form. So this is polynomial time, Gaussian elimination. This is the parity check matrix we are working on. It's Q times the identity, Q on the left, the identity on the right. Once we've got that, and this is fast, what we notice is that we could actually split our error vector according to this to the new form of H into 2 blocks, E1 and E2. The first one of weight P, and the second one is of weight W minus P. Remember, W is null. And you rewrite the equation that you have into Q times E1 plus E2 equals to S. Now Q is known, S is known, E1, E2 to find. Next thing that you notice is that E2 is small having weight. Well, it's the weight of omega minus P. The P is the number to optimize. So you will put the approximate equality between these two vectors. And once it's approximate inequality, here you may wonder, okay, how to find the solution. And the way that was proposed by Stern is it's a special way of locality sensitive function, although it was not formulated back then in this ways, but actually it is a locality sensitive function. Well, let's just project Q, E1, and S onto L coordinates, and since they're kind of close to each other, that on certain L coordinates they should be equal. So you choose the L coordinates and you search for the exact search, and this is where this exactness comes from. So this is why we pick a block, a projection block of size L, project QE1 and S, and search for E1 such that QE1 is equal to S on this block. So how do you do this search? You do the search in the meet and the middle way. So you split your E1, the one you have to find, into the left and the right part. You know that it has to be of weight P. You put in one list all the tuples E1 and QE1 of weight P over 2. And the second list, you put E1, the right E1 and QE1 plus S, and you search for the exact collision on L. And this will be your output list. And out of this output list, you will basically check whether there exists, you check for the components such that, like on QE1, so these two components for the correct solution, these two things should be E2 far away from each other. So that's the algorithm. And this algorithm heavily relies on the exact search. So here we do the exact search, and the running time for that. So this is the L out, which is just the combination of the first two lists on the size L window, on the window L, and the running time would be, the running time of this algorithm is basically the probability that you chose the correct L to project on times the running time to search for the collision. Now, classically, the running time to search for the collision between L1 and L2 would be, you simply sort L1 and L2 in time soft of size, and just search for the two values that are exact. So this is why this running time is here. It's the maximum between the up to soft O. It's the maximum between the input and the output. Now, okay, this is classical. Can we do something quantum? As I said, yes, we can. And for that, I will need to describe informally how the quantum works, how to do it, how to speed it up quantumly. Again, the goal is to find, you have lists. The goal is to find two values xi, xj, such that they form a collision in a list. And the list is because of size L. Now, classically, as I said, the running time is n. Quantumly, we do something else. Quantumly, what's called a quantum walk. So first, we create a superposition over all subsets of n of size n to the 2 over 3. These are just the subsets, just an index set. Then what we do is we upload as a quotation mark, the corresponding indices from the list. Now here is, you don't have, like, it's a generic way to describe this, but if you do it for the ISD algorithm, you don't upload, you just create the elements of your sublist on the fly because you know the age, because you know the parity check matrix age. Another thing, and you upload this on a register which is called the data register. And what you should know is that you can pre-process this register such that you can quickly decide whether this subset, which is exponentially smaller size, contains a collision. And what you would do is, well, generically you would keep it as a binary tree or radix tree or whatever structure allows you to search for exact matches efficiently. So the goal is to pre-process the list such that the collision can be found efficiently. And here comes the work, the way we search for collisions. We take each we take each index segment superposition and delete one of the index that was in I, in the set I, and add another index j which was not in the I, and we do it in a superposition. And moreover, we update the corresponding li such that it's consistent with the register that contains the index set. And again, we can do it faster because it's just adding and deleting, and if we have proper data structure and we know how to do this, this is efficient. And we repeat this process n to the 1 over 3 times. And we do again, and here we check, after we've done this n to the 1 over 3 times, we actually check whether li prime contains a collision. So this is a generalization. Well, if you know how Grover algorithm works, this is a generalized way to say that. So from Grover algorithm, except that in Grover, you've been checking. So in Grover, what you're doing is you're reflecting. You do reflections until you know that you've rotated your state such that the measurement gives you this solution with high probability. Basically, it is the same. So the second repetition is exactly the rotations, but in general, it's not clear how to rotate over the uniform superposition. And in general, if you want to do, sorry, not rotate, reflect over the uniform superposition. And in general, we can't do it better than, for this certain algorithm, we can't do it better than n to the 1 over 3. So that's from where it comes from, but basically this is Grover, or extended Grover. And once you repeat this, so this n to the 2/3 steps basically is the product of between n to the 1/3 and n to the 1/3. Once you measure with a constant probability an index set that contains a collision. So that's a generic algorithm for quantum collision search. And we can also apply it to Stern's algorithm, because Stern's, well, basically what it needs is it needs to find collisions fast, and the running time goes from this expression is the probability times the time to find the collision into the square root of the probability. That's because we apply the outer Grover times this 2 to the 1/3. Now this is what was presented to the last QCrypto, and it applies well to all the algorithms that search for the exact collision. Now the question is what to do if the collisions are not exact. If collisions are not exact, so first of all, why we can do this? So remember that this way is just was one way. So projecting on L coordinates is just one way to search for collisions. Now we can do better, and better algorithms exist to search for approximate collisions. And in that case, so these algorithms, they were presented at Eurocrypt 2015, classical algorithms. And the way they work is basically they remove this restriction on L, but instead they apply another algorithm that just searches between the L1, between the list L1 and L2 for the approximate match. And there is a formula that gives you the result that depends on the size of the list, and that depends on the approximate factor. So how far away the vector from L1 should be the vector from L2 that we search for. The way this result was phrased is not particularly well adapted to quantum walk, because it was formulated in a way that once you have two lists, here is the algorithm and there is the result, how to find the two vectors that are closest from these lists. What we rather want to have is we want to have an algorithm or an analysis of the algorithms that is formulated as follows: that given a list, we want to pre-process L such that if you receive a query vector Q, we want to find efficiently all the vectors from the list L whose distance are who have a certain distance from this query point Q. Now this is already closer to what we need for quantum walks. And these algorithms exist, and this is what This is what was known lookout-centered filtering techniques. And let me explain you how they work. So this LSF, so it's a better way to use to search for collisions, better than doing projections. So that's how they work. So this is our space. This is our F2 space. And what you do is we choose vectors, we call relevant vectors. So here I chose 10 vectors that I call C1, Ci, and they define a region. They define, so basically, I associate to each of the vector a region that contains all the binary vectors that are at distance alpha times, that are having distance alpha to the C1. So in some sense, it's not a function, but rather a relation between the C and so these regions, they will be exactly the thing that will define the hash. They do not have to be. They do not have to tessellate this space. Well, they won't because they are spheres. They can intersect. They can be holes. So in this case, it's clear it's not a function, but rather a structure. Now, the way how you preprocess the list is as follows. Well, you just associate to each vectors from the list. So here I have 13. You associate those. You associate to each. So you put these vectors into corresponding CIs. So these CIs, they will be basically the buckets. So in particular, bucket labeled C4 will contain two vectors V1 and V2. So this is the preprocessing. And you know that these vectors Vi, they are at distance alpha to the n. Now so this is the preprocessing stage. Now once you have a query point Q, what you do is you, again, search for buckets that are some beta close to your query point. Beta doesn't have to be equal to alpha. In applications it is. And what you query, upon the query you receive the corresponding vectors, CIs, so the corresponding buckets, and from these buckets you retrieve the vectors from your list. So indeed on the picture here, what you would retrieve a bucket C4. The bucket C4 contains V1 and V2, and they are close to your query point Q. And what I'm doing in the paper is I'm describing the complexity in terms of alpha, beta, gamma of this algorithm. So the algorithms are, so here is our data structure D, but just the union of all the buckets, so all these regions. Well, we have the insert function that just adds V to all the relevant buckets, so it searches for all C's. And there is a formula that describes the running time of that. We need to remove, usually we don't need to remove in applications, but for quantum walk, you remember we had to remove. So that's good to have this function as well. There is a query, which just finds all the relevant vectors with a certain distance that you described. And you can, I spare you to write down the formulas, but we have the running times as functions of alpha, beta, and the target distance gamma. Now, if you follow up the results on lattice sieving, so basically it's very close to what we do in sieving. So the best exponent for lattice sieving algorithms 292 is based on exactly the same idea, except that here we are using different metrics. That's why we have a bit different concentration results, and the formulas will look different. Now, how does it compile with quantum walks? Well, with quantum walks it compiles nicely in a sense that instead of creating data structure when we search for exact equality, meaning a tree, we'd rather put on the register with the data structure that actually helps to search for approximate search. Now, so in that case, our setup phase, remember when I created all the superposition, instead of making the data as a tree, I run the update function. When I do the step of the walk, meaning I exchange one index to another, I remove and I update, and I can do that. And then when I check for the equality approximate inequality, I do the query. that allows me to be able to apply approximate search algorithms for quantum for ISD in a quantum setting. Now, what I believe is that well, this is basically it's a classical result, so formulas are classical. I do believe they will hope to clean up and understand better the running times also for classical algorithms, for more complex algorithms. The thing I've checked, and this is what helps, so it also speeds up the quantum of search algorithms from this number to this number. Yes, it's not spectacular. The reason why it's not spectacular is, well, depending on n is big, so that kind of makes sense. The reason why the speed up is not that big is that because the LSF techniques are more powerful for large list sizes. And for the work, remember, we cut off the lists. We work with exponentially small lists, so instead of n, we work with n to the 2/3. And that's the reason why quantumly, the speed up is not that good as classical, but yet there is a result, there is a speed up, which you can find here. So I think I'm out of time. Thank you for your attention.
Okay. Are there any short questions? Seems not. Your presentation seems perfect, I guess. Okay, let's thank speakers.